We're kicking off with the basics. What microcoaxial cables actually are and why they matter. These tiny cables are the unsung heroes inside almost every high-speed device we touch. Think of them as the highways for high-frequency signals. Small, precise, and incredibly efficient. This webinar sets the stage. Structure, sizes, where they're used, and why engineers love them. By the end, you'll see why these little cables punch way above their weight. This slide is basically a collage of modern life. Drones, VR headsets, smartphones, medical devices. If it moves, computes, flies, streams, or senses, chances are it uses an I-PEX connector. It's fun to point out that our technology is inside everything from ruggedized industrial gear to the smart appliances in your kitchen. Here's our greatest hits list, the connector families that made I-PEX a go-to name. Cabline for high-speed micro-coaxial and twin-axial cables available in horizontal and vertical mating types, with optional locking feature and integrated 360 degrees metallic cover called Zen Shield to protect against EMI. NovaStack for board-to-board, EvaFlex and MiniFlex for FPCFFC, and the tiny but mighty MHFRF connectors. Mechanical locking, including auto-locking in EvaFlex and MiniFlex series connectors, isn't just a convenience feature. It's a reliability mechanism that becomes increasingly critical as pitch shrinks, data rates rise, and mechanical tolerances tighten in modern electronics. Auto-locking variants go a step further by engaging the lock automatically during insertion. EvaFlex 5 HD is fully shielded against EMI leakage by integrating full 360 degrees Zen Shield. MHF series connectors from I-PEX are ultra miniature, low profile, and lightweight RF connectors that are typically used for antenna connectivity. These connectors can support industry standard frequency bands from DC to 15 GHz. We also build ISH and IARPB series wire-to-board connectors that survive high temperature and vibration, perfect for automotive and industrial environments. Now we get into the anatomy of a micro-coax cable. The dielectric core keeps the signal path consistent and maintains consistent distance to control impedance, like keeping cars in their lanes. The outer conductor acts like a shielded tunnel, protecting the signal from noise. And the jacket? That's the armor, protecting everything from shorts and mechanical stress. Twinaxial cable is like coaxial cable's twin sibling, literally two conductors instead of one. It's perfect for differential signaling, which is why it's typically used in high-speed digital systems. Low skew and phase matching are key features. Both signals must arrive together like synchronized swimmers. The shielding and jacket play the same protective roles as in coaxial cable. Discrete cables are the workhorses, used for power, ground, and control signals. Instead of a single solid conductor, these cables typically use stranded wires for flexibility. They're rated for voltage, current, resistance, and temperature, the basics that keep systems safe. This is the simplest cable type in the presentation, but also the most widely used. Micro-coaxial cables come in many sizes, and size matters. Thicker cables give better signal integrity, but bend less. Thinner cables bend beautifully, but lose more signal. This is where engineering becomes a balancing act between performance and flexibility. Table here shows the variation in size of center conductor and outer diameter of coaxial cables with the change in AWG numbers. Insertion loss, return loss, VS, WR, and impedance are key signal integrity parameters for microcoaxial cables. Insertion loss is basically how much signal gets lost along the way in the cable. It's like trying to shout through a long hallway. The farther it goes, the more it fades. Return loss is like how much echo you get in an empty hallway. And a low VSWR means the signal glides through like a perfectly thrown frisbee. A high VSWR means the signal keeps bouncing back, like a frisbee hitting a wall and coming back at you. The characteristic impedance affects the amount of transmitted, IL, and reflected, RL, signal energies. The maximum energy is transmitted with minimum reflection when the characteristic impedance of the cable is matched to the source and receiver impedances. Shielding is your defense against EMI, and microcoaxial cables excel here. It makes sure that good signal stays inside the cable and bad signal does not get inside the cable. More than 90 decibel shielding is considered excellent. Coaxial cables have better shielding performance by design as compared to flexible printed circuits or flexible flat cables. Better shielding reduces leakage but increases stiffness and diameter. Poor shielding leads to real-world issues: display flicker, camera noise, audio buzzing, etc. Flexibility matters, especially in compact devices. Minimum bend radius tells you how tightly you can bend the cable without damage. Rule of thumb: 6 times the outer diameter. Engineers love this because it helps avoid failures in tight spaces. Twist cycles measure durability under repeated twisting. Cables are twisted plus or minus 180 degrees under load until failure. This simulates real-world use. Think foldable devices, hinges, robotics. After testing, cables are inspected for breaks and signal degradation. This slide reinforces that I-PEX offers a full portfolio of microcoaxial solutions. Different AWGs, impedances, shielding levels, and mechanical properties. Whatever the application, high speed, high temp, ultra flex, there's a cable for it. This table shows the variety of AWG sizes, impedances, temperature ratings, and losses. Cables highlighted in red can operate up to 200 degrees Celsius max. Different part numbers typically support different applications, from consumer electronics to harsh environments. A typical datasheet of microcoaxial cable shows the specifications, like sizes of center conductor, materials and thickness for insulation, outer conductor, shielding and jacket. Electrical parameters, like resistance of center conductor, dielectric strength, and characteristic impedance, along with the rated operating temperature and current, are also specified. We wrap up with a teaser for the next session, all about mechanical advantages. We'll go deeper into flexibility, bend radius, twist durability, and connectorization. Plus, we'll introduce the I-FIT solderless termination technique, a game changer for manufacturing. If today was about the electrical side, next time is all about the mechanical side.